Okay, let's go over a gas stoichiometry problem. All right. How many grams of chlorine must react to produce 16 liters of nitrogen at 1.2 atmospheres and 23 degrees Celsius? So right off the bat, I know this is a gas stoichiometry problem because I have a reaction. And understanding that stoichiometry is analyzing reactions is incredibly important for gas stoichiometry. In gas stoichiometry, I would say that the most important variable is going to become moles. Moles, or in other words, the mole-to-mole ratio between two different substances, is going to determine our bridge, right? How we can go from one side of the reaction to the other. We did stoichiometry last unit. We learned all about how limiting reactants prevent us from making as much product as we want. Limiting reactants determine how much product we can make. So in this problem here, I think we could just assume that we have excess NH3, which is ammonia, because we're just being asked how many grams of chlorine are needed to make 16 liters of nitrogen. Now in the stoichiometry unit, I would ask you maybe how many grams of nitrogen could be made. Maybe I'd even ask you how many moles of nitrogen could be made. But now here, we're told that we made 16 liters of nitrogen. So we actually are not given a mass. We're not given a mass in grams, and we're not given a mass in moles. Okay, can we still do stoichiometry? And the answer is, yeah, of course we can. We can still do stoichiometry because we have a bunch of variables that we can plug into the ideal gas law. And the ideal gas law has one variable that we really want today, which is going to be N, moles, right? I would say that moles is probably the most important variable in gas stoichiometry problems because moles are always going to be our bridge. It's how we can cross between both sides of the reaction, right? Now, like last video, I really recommend making a grocery list. Make your list of what you have and what you need to get. If you did not watch the previous video to this, I encourage you to go watch that if you want to learn a little bit more about list making. But here, really, what I'm going to just do is I'm going to write down what I know. I know the pressure of chlorine, and you could even say the pressure of nitrogen because pressure is not changing. So maybe it would actually just make more sense to just put this as P, right? Pressure is 1.20 atmospheres. Our temperature is 23 degrees Celsius. Now, just to save us all time here, I'm going to convert this to Kelvin by adding 273, and that gives you 276 Kelvin. Okay, so we have pressure, we have temperature. What are we forgetting? Well, we were given volume, but this is where I would maybe keep close track of where that volume is. This is going to be volume of nitrogen, right? And the volume of nitrogen here is 16.0 liters. So we're kind of like stationed over here on the right-hand side of the equation, okay? And I want eventually to figure out how many moles of chlorine I need. Because you can convert moles of chlorine into grams of chlorine. And for grams, I'm just going to use the letter M. M as in mass in grams. N is typically used for moles. But we still have an issue here. And the issue is that we don't know how many moles of nitrogen I have. How can I cross this bridge? If this bridge is the mole-to-mole ratio, and I have to get into moles of chlorine, well, how many moles of nitrogen do I have? So our other issue here is we don't know N of nitrogen. Okay? And that's actually a clue as to what we need to get first. We're given loads of information with one missing part. So, can you take a guess? We're using the ideal gas law. PV equals nRT. Okay? And we need to use PV equals nRT because our goal is to figure out how many moles of nitrogen we already have. All right? It's going to allow us to cross that mole-to-mole ratio, which is known. I mean, we know the mole-to-mole ratio here is 1 to 3, okay? But I can't use the mole-to-mole ratio until I'm already in moles. And unfortunately, I'm not in moles right now. I'm in liters, okay? So maybe a good way to think about gas stoichiometry is, how do you get from one of your other variables into moles, right? In this case, the variable told to us was liters of nitrogen, right? How do I go from liters to moles? So I would plug directly straight into PV equals nRT. You know, we're told that our pressure is 1.20 atmospheres. We're told our volume is 16.0 liters. And we can set that equal to N, which is what I'm trying to get. I'm not going to write the whole letter R because I'm running out of space here on the side, but it's equal to 0.08206. And our temperature, which is 276 Kelvin. Running really out of space here, but I can kind of fit it over here at the end. And you can solve for N, right? Our goal here is to get moles of nitrogen by the end of this problem so that we can it's kind of like we're paying in moles to cross the mole-to-mole bridge in order to get moles of chlorine, okay? And I mean, I guess if I were to set up all this algebra, you would get 1.20 atmospheres times 16.0 liters. We can divide that by R, which now I have space. I'm going to write out all of R. Liters, ATM, over mole K. And our temperature, which is 276 Kelvin. All right. This is just algebra. I'm going to set this equal to N of nitrogen. This is what we want. It'll be eventually in moles. Okay? And if you do all of this math, which, just to save time, I'm not going to plug that into my calculator right now, but if you do all this math, you should get a value of 0.790 moles of N2. But we're not done. All right? We only have our key to cross the bridge now, right? Because we're in moles of N2, but I'm trying to get to moles of chlorine so that I can eventually convert them back to grams. Honestly, whenever you see a gas stoichiometry problem and it mentions anything about grams, that should be at the back of your mind. That's just one conversion. How do we convert between moles and grams? You use molar mass, right? Let's just deal with getting from this side over to the left side, right? I'm going to switch over to orange here. And really now we're just doing what you should know by now, which is good old-fashioned stoichiometry, the mole-to-mole ratio. And I want to get into moles of chlorine. Well, using the mole-to-mole ratio here, we have 1 mole of N2. We have 3 moles of chlorine. And if you do this, you should get a value. Oh wait, hold on. I forgot. We can actually do this all in one sweep. All right. Now, if you want to, you could get directly into moles of chlorine. Whatever you plug in your calculator here would be moles of chlorine. But we also learned in the stoichiometry unit that you can go from moles to gram just by doing another conversion, right? When we go moles to grams, we're taking the molar mass of chlorine. And the molar mass is always 1 mole, right? the molar mass of chlorine here is going to be 70.906 grams. And you can find this on the periodic table, okay? Well, actually, you would find 35.453, and then you got to multiply that by 2 because we have 2 chlorines. It's diatomic. So maybe it just helps for me to kind of just show here, you know, our conversion factor here is we did the mole to mole ratio. And over here, we did molar mass. In other words, it was gram conversion, right? It's like how we got into grams. And if you solve for all of this, I mean, maybe it helps to see how units get canceled out. If you solve for all of this, your final answer here would be 168 grams of chlorine, okay? So in summary, because this is a long video at this point, you know, gas stoichiometry is how do we cross this bridge? How do we cross the reaction bridge? Use the mole-to-mole ratio. Gas stoichiometry is also about how we use the ideal gas law to solve for moles, to solve for N. I would assume that almost every gas stoichiometry problem somehow involves the letter N, because gas stoichiometry is all about using the mole-to-mole ratio. And then cherry on top, which is just a conversion. Sometimes you may be asked to convert between moles and grams. Maybe your given pressure is not in atmospheres. Maybe it was in torr, or maybe it was in millimeters of mercury, and you would have had to convert that. I mean, our temperature here was given in degrees Celsius, and I had to convert that to Kelvin. Luckily, Celsius conversions to Kelvin are kind of easy. You just add 273. But it can get more difficult if like pressure needed to be converted. Volume, maybe the volume could have been given in milliliters, right? Maybe if you wanted an even more complex problem, you could have been asked how many liters of chlorine must react to produce 16 liters of nitrogen. And in that case, you would actually have to use the moles of chlorine and plug back into PV equals nRT to solve for whatever volume of chlorine you're trying to get. Really, all I'm trying to say here is this, which is that the ideal gas law is what we're now throwing into all of our stoichiometry. The ideal gas law is how we can bounce between pressure, volume, moles, and temperature. It's crucial to all of the conversions that we do, okay? And while gas stoichiometry problems can come in a whole different variety of flavors, I think the basic thing here is how do you cross the bridge, the mole-to-mole ratio, and keep a grocery list. Pay attention to what you need and what you're trying to get to, because you almost for sure are always going to be using the ideal gas law. I hope that was helpful.